be better now. Can you hear me now, Mustafa? Okay. Let's see. Is the text visible on the screen? Perfect. All right. Let's get rid of this. Okay. Are we expecting more people, or should I just begin? Okay, so chapter 4 is done with. There is one thing remaining in chapter 3 that I skipped and posted a video about, and I'm just going to go through it because I think it's important and I want you to do it. So that's something that we'll do today, 3.6.2, which is the Rank-Nullity Theorem, and we'll do basically the I think section 5 or section 6, where it's about row space and column space, and we'll do that. And after that we'll do 5.1 as much as we could, which is about the orthogonality in Rm. Okay. So that's something that we'll cover today. Okay, so let's just begin. Oops, didn't mean to do that. Okay, so still getting the hang of this. Okay, so let's define a few things. So the definition of a row space is the vector space spanned by the rows of a matrix, and the column space, so the column space is the vector space which is spanned by the columns of a matrix. Okay. Alter the syllabus. We'll talk about this at the end of the lecture, Mustafa. Okay. So here we go. There was I. Okay, so let's suppose you have a matrix which is an m by n matrix, and so it has, let's suppose, m rows and n columns. So each row, let's suppose if you consider this row, this row, this row, this row, this row, whatever. So there are m rows, and so the row space, each row, let's suppose I take this row, and so the first row is, let's suppose, A11, A12 up until A1m. Then if I make a vector out of this, if I consider this to be a vector, the first row is a vector, and the second row as another vector, A21, A22, dot, 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 A2, n, it should be n, and so on. You will have m rows. Now the question is, are these m rows independent or not? Are these, if we make vectors out of these, so let's transpose them. And so the question is, if I take these row vectors and they will either span, so the idea is these rows will form a subspace of Rn. They will span the entire Rn if they are linearly independent, and and if there are as many vectors that they're required, but they will form some subspace of Rn because there are n vectors. So each of these vectors has n elements. Secondly, the columns will form a subspace of Rm, and that's precisely what we call the row space and the column space of the matrix. Okay. All right, so here's the thing. We have a theorem, nice little theorem, which tells us that equivalent matrices have the same row space. Just make sure that you remember what equivalent matrices are. So equivalent matrices, oops, didn't mean to do that. Anyway, that's fine. Equivalent matrices are those, so A, B is equivalent to A if we can express B as some ek minus 1 dot 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 e1 A. So if you can transform where these are elementary matrices. So if you can perform a bunch of elementary row operations on A, and if it becomes matrix B, then matrix A and matrix B are said to be equivalent. And so the idea is that equivalent matrices have the same row space. Okay. The next idea is we define the rank of a matrix, and the rank of a matrix, so the rank of a matrix is the dimension of its row space. So if the row space is n dimensional, the rank will be n. So for example, this, remember, the dimension is equals to the dimension of a space is, let's suppose, V is equals to the number of basis vectors. Okay, so that's the definition of a rank. You find the dimensions of the row space, and then that's your rank. We'll do an example in a bit to make it more explicit what we're talking about. Okay, and the other thing that we have is called the nullity. So the nullity is actually the dimension the dimension of the null space of A or whatever. Okay, so the dimensions of the null space. So this is in context of some matrix M by N matrix A. Okay, and so the rank is the dimension of the row space. So let's just write it down. Rank is the dimension of row space, and the nullity is equals to the dimension of the null space. Okay, and what's the null space? The null space is all of those vectors that are, so the null space, if you recall, the null space is the space of all vectors that are mapped to 0 under A. Notice that I'm using some linear transformation, but the idea is simply it is the solutions. It is basically the solutions of AX equals 0. So if this has only trivial solution, then the null space just has the vector 0. Okay, so it's possible that your null space could be 0 if AX equals to 0 has only the trivial solution, and the null space could have perhaps some other collection of vectors if you don't have just the trivial solution for this. Okay. All right. So that's the rank and that's the nullity. Okay, before we do some theorems, I would like to actually go through just a bit of an explanation of how do we find the dimensions of the row space and how do we find the dimensions of the column space. So let's take an example, and so here is an example. Okay, so let's suppose we have the matrix A. Matrix A is equals to 1, 2, minus 1 and 1, 2, 4, minus 3, 0, and 1, 2, 1, 5. And so the idea is that the row space, if I call this first row as R1, this second row as R2 as vectors, and the third row as R3, notice that all of these are in R4 because they have 4 entries, 1, 2, minus 1, 1, 2, 4, minus 3, 0, and so on. And so these are 3 vectors, and so the collection is, so the idea is that the row space is going to be equal to the span of R1, R2, and R3. And so we need to figure out what space do these vectors span. And so the answer, the solution rather, is given to us by this theorem, that is, equivalent matrices have the same row space. So if I can convert this into its row echelon form, so the idea is convert it into its row echelon form, and we know that the row echelon form is done by just doing some elementary row operations. And so I'm taking this example for the book, so I already have the row echelon form. You can check it out that the row echelon form for this matrix will be 1, 2, 0, 3, and 0, 0, 1, 2, and 0, 0, 0, 0. And so if they have the same row space, then the row space of this is simply, if I call this U1 and if I call this U2, then this is simply the row space for this case is simply the span of u1 and u2, right? Okay, and so because the third vector isn't going to span anything, if you multiply it by any, if you take a linear combination, it's not going to add to anything. So we don't have three vectors in the span, we have only two vectors, and actually, so the row space of A, so I can say that the row space of A is equals to the span of 1, 2, 0, 3 transpose and 0, 0, 1, 2 transpose, because I'm guaranteed by the theorem that these two will have the same row space. And so since it's spanned by this and both of these are linearly independent, notice that when you convert it into row echelon form, the remaining vectors are bound to be linearly independent. If they were linearly dependent, they would have become 0. This row was linearly dependent on either the first one or the second one or both of them, and it was converted into 0. After you convert it into row echelon form, there is no linearly dependent row. So both of these are linearly dependent, both of them span, and so this collection U1, U2, this is a basis for the row space of A, and since we have a basis, then the dimension of the row space is equals to 2 because it has just two vectors. And so this is how you find the dimension of a row space. That's the first thing. The second thing is, how do you find question, how do you find the dimensions of the null space of A? And that's easy. You figure out which of these vectors are taken. All you need to do is to figure out the solutions for Ax equals 0, and we've done this in one of the previous classes. Okay, so you just need to figure out which of these vectors will be mapped onto 0, and once you have that collection, that will be the dimension of the null space of A. Okay, so that would give you the nullity. All right, so here's a theorem. We have the first thing, that the system Ax equals B is consistent. This is a consistent system if and only if we have B is in the column space of A. And this is trivial rather, because we know that what we are saying is this Ax, of course Ax can just be written as a linear combination of the columns of A. So xi, ai, where ai's are the columns of A, and since this is a linear combination, all we're saying is that B is in the column space. So the column space is given by the linear combinations of these columns, and so if vector B is in the column space, then you will have a solution. So consistent means having a unique solution. Okay, where A is an m by n matrix, X is in Rn, and B is in Rn as well. Sorry, B should be in Rm. Okay, that's the first one. The other one is that, actually let's move to the other page. All right, so theorem, we have let A be an m by n matrix and Ax equals b, then Ax equals b is consistent for every b. Now, in the previous theorem, we were just looking at when will it be consistent for this specific b, and the answer is when b is in the column space. Now, if you want it to be consistent for every b, then the idea is that every b must be in the column space. And if every b is in the column space, then the implication is easy. This will only happen if and only if the column space of A spans Rm. Because if it spans the entire Rm, then whatever vector you give it, it will be able to find a solution. It will be able to get to that vector using some linear combination of the columns of A. Okay, and so if you want a solution for all of them, then this must span the entire Rm. Okay, and I'm not doing the proofs of this theorem. These are provided in the book. You can go check them out. Okay, and if we consider these theorems for an n by n matrix, then we have the following. If A is an n by n matrix, then A is non-singular if and only if the columns of A form a basis for Rn. Now, this is just the previous theorem taken for an m by n matrix, and so it's simple to see, because when you have a matrix which has n rows and n columns, then if I multiply it with Ax equals b, this is in Rn, of course, and this is also in Rn. This is n by 1 and this is n by 1, sorry. And so the column space of A must span Rn in this case, because m and n are equal. And so if n vectors span Rn, then of course you have a basis, because for an n dimensional space you need n vectors. So thus you have a basis for Rn. So these columns, one particular basis for Rn will be all of these columns of A. Okay. All right. Okay. All right, moving on. So at this point, we bring in the Rank-Nullity Theorem. None of these are just some trivial samples, and now we have the Rank-Nullity Theorem. And here what it says if A is m by n, so you have an m by n matrix, then rank of A, that is the dimension of the row space, plus the nullity of A is going to be equals n. And so you get a simple equation, that is the rank plus nullity equals to n, where n, notice that n were the columns of A. So that's the Rank-Nullity Theorem. Okay, and so let's check this out. So just a little bit of, again, this was the dimension of the row space, and this was the dimension of the null space of it. And let's look at an example and verify. Again, I'm not doing the proof, I'm just going to do an example. Okay, again, let's consider the same matrix, which was 1, 2, minus 1, 1, and 2, 4, minus 3, 0, and 1, 2, 1, 5. This was the matrix A, and the row echelon form of this matrix was 1, 2, 0, 3, 0, 0, 1, 2, and 0, 0, 0, 0. So this was the row echelon form of that matrix. And so now if we're trying to find the null space, notice something. If I take this row echelon form, so I have 1, 2, 0, 3, 0, 0, 1, 2, 0, 0, 0, 0, and if I try to find the solution ux equals 0, then that's simply because if it was ax equals to 0, I can perform some elementary row operations here and an elementary row operations here. This will become 0, still remains 0, and this will become u. And so if I try to find x1, x2, x3, this equals to 0, 0, 0. Notice that what I will have to do is I will have to pick x3 as a free variable. My second equation will give me, sorry, I need to have 4 over here. This is, there needs to be an x4 here as well, because this is 3 by 4, and so this will be 3. Okay, and so x3 and x4 both will be free variables. Once you have that, you have the equations. Actually, hold on, let me just, this is x3, this is x4. Let me write these equations first. The first equation is saying x1 plus x2 plus, the first equation is saying that x1 plus 2x2 plus x4 equals 0. The second equation is saying x3 plus x4 is equals to 0. So you have two equations, and now you can pick x4 and x2 to be free. So if you pick x4 to be free, let's pick these two. And the way we pick these two is we check the ones that we won't pick are the ones which have leading 0. So this has a leading 0, sorry, this has a leading 1, and this has a leading 1. This one does not have a leading 1, and this one does not have any leading 1. Okay, so this, because this is the form of the matrix, this has a leading 1, this column, and this column has a leading 1. So 1 and 3 are will be left as it is, and 2 and 3 will be set as, 2 and 4 will be set as free. So this column and this column tells us that x2 and x4 will be free. So I choose x2, x4 to be free. And using these two equations, I get the following. I get x3 equals minus x4, and I get x1 is equals to minus 2x2 minus x4. And so if I write this down in a addition notation, what I get is the solutions of my null space x1, x2, x3, x4. These are given to me by x1 is simply minus 2x2 minus x4. Then x2 is free, so I just set it as x2. x3 is minus x4, and x4 is free. I just set it to x4. And now I can rewrite this entire thing as follows. I can say, let's separate x2, so this was minus 2x2, this one had x2, this one did not have an x2, 0 times x2, and this one did not have an x2 as well, plus another vector that contains the x4 terms, minus x4, 0 times x4, minus x4, and 0 times x4. And so these can be written as x2 times minus 2, 1, 0, 0, plus x4 times minus 1, 0, minus 1, 0. And so this is your null space, right? So this gives me my null space, because these are the solutions. All vectors v equals to in the null space will be of this form. And so what this tells me is the following, that if I call this vector v1 and v2, then v1, v2 is a basis for the null space of A, and therefore I get the dimension of my null space to be equals to 2. Okay. All right. Now here's something that we need to check. Let's check whether the rank-nullity theorem holds. Now the rank-nullity theorem told me that rank plus nullity should be equals to n, where A is an m by n matrix. So for this example, we've already done the rank. The rank, oops, where did it go? Sorry about that. Okay. And so we have we've already done the rank for this example. The rank in this case was, where is it? Okay. And so the rank, we found the dimension, the rank is the dimension of the row space, which was 2. So for this example, we have found the rank, which is equals to 2, and plus we have also found the nullity, which is equals to 2, that is the dimensions of the null space. So these were the dimensions of the row space 2, dimensions of the nullity is 2, and this is equals to 4, where notice that the matrix that I was dealing with was a 3 by 4 matrix, so 3 by 4, 3 by 4. And so rank plus nullity should have been equals to 4, and indeed that's true, that the dimensions of the rank and the dimension of the nullity is equals to 4. And this perhaps we can think about this in terms of the vector space. So we have two things. We have row space and we have the null space. And so this is spanned by two vectors. This is spanned by two vectors, let's say R1, R2, let's say U1, U2. And the total dimensions of these, so if I take the dimensions of this space and the dimensions of this space, and if I add them up, that's equals to the column of A, which is interesting. And actually that's not the only interesting thing. There are many interesting things that we can notice about a matrix. So here are a few facts. So if we consider the matrices, let's just talk about this example matrix from now on for now. A and U, where A was the 3 by 4 matrix that we were dealing with, and U was its row echelon form. Then there are a few facts to notice. The first one is that A and U have the same row space, which we already saw as a theorem, but A and U have different column spaces. So the column spaces will be different. But that's not all. We have, even though the column spaces are different, the dependency relations between columns of A are the same as the relations between columns of U. And what are these relations? Let's write the matrices down again. 1, 2, 1, 2, 4, 2, minus 1, 3, 1, 1, 0, 5. This is matrix A. Matrix U is 1, 2, 0, 3, which is of course just the row echelon form of matrix A. And this is 1, 2, 0, 3, 0, 0, 1, 2, and 0, 0, 0, 0. Notice that if I write this now, I'm not looking at the rows, I'm looking at the columns. So let's consider this to be U1. Actually, for the sake of confusion, let's call this C1. So column 1, column 2, column 3, column 4. Notice that column 2 is equals to 2 times column 1. And you can also check that column 4 is equals to 3 times column 1 plus 2 times column 3. You can verify these relationships of the matrices that we have. Okay. Now these relationships are exactly the same, even though they have different column spaces. The column space spanned by this matrix will be different than the column space spanned by this. But the relationships are the same between the columns. So we have, if I call this D1, D2, D3, D4, these are the columns that I'm picking, then D2 is equals to 2 times D1, and D4 will be 3 times D1 plus 2 times D3. Okay. Give me a little, I'll be right back. Okay, sorry about that interruption. Okay, so that was the first interesting thing about these columns of A and U. The next thing is as follows. Here's the next fact, that the dimensions of the row space of the transpose of A. Notice that this is not for just this example, this is true for any matrix, that if you take the transpose, then the rows becomes columns and the column become rows, then the dimensions of the row space of AT will be the same as the dimensions of the column space of A. Right? So if you just take the transpose, actually not just the dimensions, even the entire space will be the same, because it's just the same, spanned by the same vectors, it's the same set of vectors, right? And the row echelon form of A tells us which columns of A will form the basis of the column space. So notice that even though for the row space it's the same, for the row space we just look at for the row space it's the same. For the row space all we need to do is look at the rows and they give us the basis. But for the columns, for the column space, it's a bit different. We have considered this matrix U tells us which columns to pick to find the basis for the column space. So it tells us that this column and this columns have the leading entries, which means you take the first column and the third column to find a basis for this matrix. Okay? And so the idea is that if you want to find the column space of A, all you need to do is check which of the columns are independent, which one of them have the leading entries, and you just take those as the columns. So the column space of A is given by the span of the first two, of the first and the third. So here it is. The first column is 1 to 1 and -1, -3, 1. So 1, 2, 1, -1, -3 and 1. Okay. So this is the basis. So if I call this was D1 I think, and this was D3, then D1 and D3 is the basis for A. So slightly different for the row space and the column space. For the row space you can just pick out the rows of U and you have a basis. For the column space you check matrix U and it tells you which columns to pick from A, and that gives you the basis. Okay, so there's a slight difference. Okay, that's it from the from 3.5. So this is it for the rank nullity theorem. We'll move on to now the orthogonality. So this is chapter 5 now, 5.1, which is orthogonality, and over here we're going to talk about the scalar product and so on. So this is orthogonality. Okay. Okay, so the scalar product. Okay, so consider now we're talking about Rn, but let's limit our conversation to perhaps R2 and R3. Let's suppose we have some vectors x and y. So let's suppose x is a vector, x1, x2. Actually, we don't even need to do that. Let's just talk about a general Rn. So if x has n entries, so x was a vector and y was also a vector from the same space, yn, then the scalar product, we've done this before, but we're doing it again. The scalar product xty is defined as x1, y1. This is just the dot product that you've seen before, I'm sure, in other classes. x1, y1 plus x2, y2 up until xn, yn. And for, you should already know that in R2 and R3, what you have is the Euclidean distance when you find Euclidean distance. So this is the length. If you're trying to find the length of a vector, what you do is x1 squared plus x2 squared. This is the length of this vector in R2 or in R3. For R3, you would have one more entry. But actually, this can be just written as, this is x1 dot x1 plus x2 dot x2. And of course, this is nothing but if I take matrix X and take the scalar product with itself. So X transpose X. So this is nothing but X transpose X raised to the power half. And that's true for R3 as well. Okay. And so that's one thing. The other thing is, of course, that the distance. So distance, if you want to find the distance between two vectors, then x minus y is simply, again, you just do x dy to this raised to the power half, which is nothing but, of course, x1 minus y1 whole squared plus x2 minus y2 whole squared. And if you had an R3, then you would have another. So this is the distance between two matrices. So this was the magnitude, and this was the distance. Okay. And some familiar properties that I am sure that you will be aware of, which are that x dy is symmetric, which is y dx. That's easily checkable. Another thing, that x dy can be written as, in R2 and R3, you must have seen that you take the magnitude of x, take the magnitude of y, and multiply it with cos theta, where theta is the angle between x and y. Okay. All right. And if you want to find, let's suppose x was a vector, and if you want to find the direction of x, if this is the direction of x and this is the direction of y, let's call it v, then u is simply nothing but the unit vector defined in the direction of x, and y is nothing but the unit vector defined, then v is nothing but the unit vector defined in the direction of y. So I'm doing nothing but I'm dividing x with its magnitude and y with its magnitude, and you must have seen this. These are the unit vectors where u is in the direction of x and v is in the direction of y. Another familiar property is your Cauchy-Schwarz property, which is evident from this, that is x dy, that the scalar product is going to be less than or equals to the magnitude of x times the magnitude of y. Okay. All right. And lastly, this is the reason we say that two vectors are called orthogonal if x dy, if their dot product is 0. So if the dot product is 0, you call them to be orthogonal vectors. Okay. And this should all be familiar to you from your other classes. Okay. All right, and so the idea is we want to expand, generalize this idea. We want to generalize this and we want to generalize this idea to Rm. Now we're no longer talking in R2 and R3, we're talking about all of these ideas in Rm, and the idea is the same, is that if you have some vector in Rm and another vector in Rm, let's make this n, and so x, t, y, even if they're in Rn, if their inner product is 0, if their scalar product is 0, you call them to be orthogonal. So x and y, xy are orthogonal. And so these ideas are easily generalizable to vectors that have more than 2 or more than 3. The only problem is you won't be able to visualize them, right? But the idea is the same, because they're in higher dimensions, you can't visualize them, but it's the same thing. And so we want to generalize this concept of orthogonality, which we'll do in a bit. So let's just talk about the scalar and the vector. So scalar and vector projections. Okay. And so the idea is as follows. Let's suppose you had two vectors, vector x and another vector y, and what you wanted was the component this is the component of x in the direction of y. This is also called the projection, and the way to find this projection is as follows. Let's call this projection P. Okay, and so it's very easy to find P if you can find the direction in which y is going. So you need two things to define P. The first thing is you need the direction, and the second thing is that you need the length alpha. So if you have the length and if you have the direction, you can scale this direction with this length and get P. So a simple equation for P can be written as P is nothing but alpha times u, because we are saying that u is a unit vector, and unit vectors have length 1. So if I multiply u with alpha, then P will get length alpha, and it will be in the direction, it will be parallel to u, but will have length alpha. So we'll get this projection vector. And the way to do that is as follows. So here's how we do it. The idea is, let's find alpha first, and alpha is easy to find. Alpha is simply you take the magnitude of x and you multiply it by cos theta. This is nothing but basic trigonometry. If this is your vector x and if you want to find this, then this is just you find if this length is magnitude of x and you want to find this, if this is the angle theta between them, let's suppose this is the angle theta, then this is nothing but x cos theta, and this length is x sine theta. I am interested in the horizontal part, so alpha is equals to x cos theta. And if I now notice that you already have some part of the definition, recall that xty is simply absolute value, the magnitude of x, magnitude of y times cosine theta. I already have magnitude of x times magnitude of times cosine theta. All I need is magnitude of y. So if I add in, if I multiply magnitude of y here, now I of course can't do something like this without compensating for it. So if I'm multiplying it, I'm dividing it as well, and the way to do that, now this top thing just becomes xty, that is their scalar product, and it's divided by the magnitude of y. So that's how you find alpha. Next thing you want to find in P is u. U is simple. U is just the unit vector in the direction of y, so that's v y. And so at this point you are in the position to find alpha times u, which is xty over y, magnitude of y, times y over magnitude of y, which is, this becomes xty divided by, this is magnitude of y whole squared times vector y. And notice this magnitude of y, if you recall, then magnitude of y is simply yty raised to the power half. So that means if you square it, then that's just yty. And so P is simply x transpose y divided by y transpose y times y. And so this is vector P. And so let's just write these down. Alpha is called the scalar projection of x onto y, and P is called the vector projection of x onto y. And the formulas are alpha equals to xty upon magnitude of y, and for P it's xty over yty times vector y. Notice that the scalar product is a number. This is a number, this is a number. So again, the idea is we were looking for some scaling in the direction of y, and so P is of course going to be parallel to y. And what we've essentially done is we've written P as some beta times y, where we've just scaled this vector y and made it of this length so that it's in the same direction, but this is just simply P equals to some constant where B is given by this number. Okay. All right. So I hope that's clear. Okay, and just to complete the lecture, again, all of this is, we're talking about Rn now. So all of this is generalizable to Rn. So even though you can't visualize it in Rn, the ideas is still the same, the formulas are still the same, and it works. Okay. And one last thing before we finish today's lecture is, remember the cross product. If you find the cross product of two vectors, scalar product is something we did, cross product is found by this, you would have already done it. Let me just, I'm not defining it, but I'm telling you how to compute it. You compute it by finding the determinant of this matrix, x1, x2, x3, and y1, y2, y3. This is how you find a cross product. This is not the definition of a cross product, but this is just how you find it. And if you want to define it, it's just simply x cross y is equals to x2, y3 minus x3, y2 of I minus x1, y2 minus x, oops, I have made a mistake over here, x1, y3 minus x3, y1 j, I'm finding the determinant of this matrix, and finally plus, this is, if you hide this, then this is x1, y2 minus x2, y1 k. And so this is the cross product, and the cross product, what it gives you is, if you have a matrix, if you have a vector x and if you have a vector y, then this cross product of y will give you a vector that is orthogonal. So x cross y gives you a vector that is orthogonal with x and orthogonal with y. So x cross y transpose x should give you 0, and x cross y transpose y should also give you 0. That is, they are both, this vector is perpendicular to vector x and vector y, both of them, right? So this should hold for a. Okay, and that's it for today's lecture. This was nothing new. I hope this was all a review of some of the things that we've done before. I'm sure you've seen scalar products and distance and all of this. Maybe projection is something that you're seeing for the first time. Sometimes even those are covered, but this cross product should be nothing new. So we're just building the blocks for the next few sections. And that's it for today. Let me know if there is anything that you are unsure about or any queries that you have. Mustafa was asking if I will alter the syllabus. The idea is that the material that I'm covering now, I will not be doing proofs of theorems, I'm taking them out of the official coursework. I'm taking it out of the official classes because we don't have as much time, and so I'll just be naming few theorems. Previously I used to go through each and every theorem, prove it and get a sense of it, but now I'll just be stating them and using them. I don't want to alter the syllabus too much because I don't want to hurt the integrity of the course, and so generally the course will remain the same, with a few things perhaps dropped here and there, some proofs dropped here and there, just to save time. Let me know if you have any questions other than that. I'll hang around for a couple more minutes before I end this stream. Okay. Thank you, everyone. Have a good day. Bye-bye.